All right. Good afternoon, everyone. I hope you are all very well. In this lecture, I'm going to talk about the design of flexible pavement. But before that, if you remember, in the previous lecture, we talked about the design traffic as the load applied to the flexible pavement. So this is one of the input data we need in order to design the flexible pavement. I explained you how to determine the damage index and also the number of repetition of the load for the design life of the pavement you want to design. And there was one example left that I'm going to solve it here for you. So before I start the lecture, can you please let me know whether you can hear me well, whether the quality of the voice is fine or not? Great, thank you very much. Thanks. So last week I solved one example and we used some presumptive value to determine the design traffic. This is a more important example that I'm going to solve you here. In this example, we are going to use the survey data. So it's a way in motion survey data that we are going to use. So based on the survey data, we know how many heavy vehicles pass through the road during the design life of that one. So based on the survey data, we have the value for average annual daily traffic. The classes of the vehicle passing through this road are class 8, 9, 10, and also 3, 4, and 5, based on Ostro's classification. And we also know how many heavy vehicle pass through the road based on the data. Now we want to determine the design traffic, and later we are going to use that data traffic for design of the pavement. So these are the assumptions we are considering in this example. The design period is 20 years, the design life of the pavement. The growth rate is 4%. The road that we are designing is a 2-lane dual carriageway. Also, it's an urban road, and it's a single direction count. So the values that we have is for one single direction. Now, based on the design period and also the growth rate, you can calculate the cumulative growth factor, which is used in order to determine the design traffic for the whole design life. So this is the equation that we have from statistics, right? You can calculate the value of cumulative growth factor. R here is the rate of growth, and P here is the design life. And we already know the values. The value of annual growth rate is 4, and the design period is 20 years. So you can simply substitute in the equation, or you can use that table that I provided you during the lecture in order to calculate CGF. Very simple. It is around 30. The next traffic parameter that we need is determination of direction factor, or DF. What is the meaning of this DF? That depends on whether we are dealing with a one-way road or two-way road. So here we know that the survey data is for single direction. So everything that we have, all the input data are for one-way direction, for single-way direction. Therefore, DF here becomes equal to 1. The other one is LDF, or the lane distribution factor. For lane distribution factor, we are going to use this table, the presumptive value. What does this mean? It means that when we are designing a pavement, we are calculating the pavement design traffic for one specific lane. And generally, that lane is the outside lane or curb lane. And in Australia, it's the left lane. So based on asked roads, for rural road, which is the case for this example, if we are dealing with a two-lane road, then we need to give LDF equal to 1. It means that we assume all the heavy vehicles are passing through the left lane. And this is a valid assumption that we are considering. But if you have data for different lanes, then you can determine the value based on the survey data. But here, since we don't know what is the distribution for each lane, therefore we are using the presumptive value. So we give all the heavy traffic to the left lane or curb lane. Therefore, LDF becomes equal to 1. Now we want to determine the number of the axles, the axle load group. And we have the survey data. So for class 3, with 3, we know we have 300 units, or we have 300 vehicles for one day. The first one, the first axle here, is a single axle, single tire, the front axle. So we have 300 single axle, single tire for this class. And also for class 3, we also have 300 single axle dual tire. So we write it 300 and 300. For the next class, for example, for truck class 10, this is the vehicle. So we have 20 units or 20 vehicles passing through the road during one day. So it means that we have 20 single axle, single tire. We have 40 tandem axle dual tire, and we have 20 triaxle dual tire. So 20 single axle, single tire, 40 tandem axle dual tire, and 20 triaxle dual tire. And we can do the same thing for the other classes. So now we know how many axles are passing through the road during one day. Now we want to know how many axles are passing through the road during its design life. So first we multiply the results for per day, the AADT, with 365, and after that we multiply it by cumulative growth factor to determine the number of the axles per design life of the pavement. So this is just simple multiplication with 365 and also CGF, which is equal to 29.78. So these are the number of the axle passing through the road during the design life. But as you look at here, this table doesn't give us any information about the weight of the loads. So far, we just work on the number of the axles. No information about the weight. In order to add the effect of weight, we need to use the load distribution, right? The traffic load distribution. So this is the presumptive load distribution that we need to determine. But before that one, I should also tell you how we can determine NDT, the traffic parameter, and the number of the axle group per heavy vehicle. So NDT is the number of the axle groups, right? So simply, you can get the summation of these values that we derived in the table. The summation of these will give us the number of the axle groups passing through the road during its design life. So it becomes 1.62 times 10 to the power 7, heavy vehicle axle group. And you remember this parameter from the previous lecture. It is the number of the axle group per heavy vehicle, the average number of axle group per heavy vehicle. So you can simply calculate this one based on NDT divided by the number of the heavy vehicles, right? So NDT divided by number of the heavy vehicles. This is the number of the heavy vehicles. And the number of the axle group per heavy vehicle becomes 2.3. Now, as I mentioned, this won't give you any information about the load, the magnitude of the load passing through the road. So again, based on the traffic data that we have, we can determine the distribution of the load for each axle. So what is this table? The information that we get from this table is that, for example, here, it means that 6.5% of single axle dual tires carry the weight of 70 kilonewton, approximately 70 kilonewton. Or for example, here it means that 14.42% of tandem axle single tires carry the weight approximately equal to approximately 100 kilonewton. Right? So this now gives us some information. And the summation of these percentage becomes 100, of course. Now the thing we can do is that we know how many single axle dual tire we have, right? So for example, for single axle dual tire, the number passing through the road during the design life is 3,260,700. So you can simply multiply that with these percentages to determine the value of the single axle dual tires with the weight of 70 kilonewton, for example, right? And the summation becomes equal to the number of the single axle dual tires. So I explain it once more how we determine this one. It is simple. 6.5% of single axle dual tires carry the weight of 70 kilonewton. And the number of single axle dual tires is 3,260,000. So you can simply multiply this 3,260,000 with 6.5%, and that will give you 211,000 or 212,000 approximately, which means 211 or 212,000 single axle dual tire with the weight of 70 kilonewton are going to pass through the road that you are going to design. But still, this is not enough for us. You remember, the main philosophy in Ostrods is to convert all the traffic data to the standard axle group and the standard axle load, right? So we need to convert everything to the standard load. You remember what is the standard load from the previous lecture? It is single axle dual tire with the weight of 80 kilonewton. This is the standard one. How can we convert these to the standard value? We have one empirical equation. So it is load over the standard load to the power 4. And this is for the mode of rotting or permanent deformation at the subgrade level. I explained it in the previous lecture. So we have the value of the single axle dual tire with 70 kilonewton. Now we want to convert it to the standard load. What we do is that we multiply this 212,000 with 70 over 80 to the power 4 in order to convert it. And the value that we get becomes 124,239. So 212,000 times the ratio of the load over the standard load to the power 4. Now you converted everything to the standard load. And the unit for that is ESA, the equivalent standard axle. So you can calculate the summation of all these values and determine the design traffic, DESA. So this is your final design traffic. For which mode of failure? For rotting or permanent deformation. And we generally calculate the damage index. Damage index is the value of the equivalent standard axle over the number of the axle group per heavy vehicle, right? Or heavy vehicle axle groups, or NDT. So the design traffic over NDT will give you the value of the damage index. And we generally show the results like this. The damage index is 0.73. So is this clear how we determine the design traffic? All right, if you don't have any questions regarding the example, now I'm going to explain about the next step of the project, which is determination of the design traffic. So as you know, as I explained in the project description, we are going to design a pavement, an access road to the port, and there is one existing traffic on that road, right? And I provided you with the survey data for that road. I gave you the road traffic counts as well as the traffic load distribution. But now, because of the development of the port, we will have some additional traffic. So more heavy vehicles are going to pass through that road in order to transfer and carry the containers, right? So eventually, when you want to determine the design traffic, you need to take into account the effect of the existing traffic, and of course, the growth rate of the traffic during its design life, as well as the additional traffic because of the development of the ports. And finally, determine the design traffic, the total design traffic for the road. So let me show you the survey data that I provided you. In the Excel file, we have the traffic data. In the second tab, we have port road traffic counts. So these are, again, real survey data, WIM, weigh in motion data that I provided you. So this is for a case of January to August 2020 for one road, and the approximate rate of growth, or R, is 3% here. So here you can see for different classes of vehicles, what are the number of the, or what is the average daily traffic, right? This is for weekdays, this is for Saturday, and this is for Sunday. And the road is a two-way road. This is for southbound median lane. So there are two lanes for each direction. This is for southbound curb lane. This is for now northbound median lane and northbound curb lane. So you have weigh in motion survey data regarding the type of the vehicle passing through the road. Also, I provided you, because here we don't have any information about the magnitude of the load, right? The weight of the loads. So now, in order to get some information about that one, I brought you the presumptive values for different states. For example, this is the traffic load distribution for urban roads in New South Wales, for a road in New South Wales, and it will give you the information, the percentage of each axle passing through the road. For example, here, if you can see, it means that 12% of single axle dual tire passing through the road are carrying the weight of 70 kilonewton. And you can decide about the load distribution based on your group number. For example, group number 1 to 11 should use the load distribution for New South Wales. Group number 12 to 22, load distribution of Queensland, WA, as well as Victoria. This part is for existing traffic, right? For existing traffic, this is the current survey data that we have for one specific road. Now the thing we want to do is that since we are going to develop one port, we should expect that the traffic will increase for carrying the containers. So here are the information provided for the containers. So we have two groups of containers, the one imported to the port or the one exported from the port. And two different sizes, 12.2 meter and 6.1 meter. These are two very common type of containers. Number of the container per day, it is 40 import and 60 export. And this can be split between the large containers and small containers. And that's the function of your group number. For example, if your group number is 10, this becomes 40%, 12.2, and 60%, 6.1 meter. And for container, here are the information about the load. For example, for container with the size of 12.2 meter, or the length of 12.2 meter, for the import case, 2.3% are carrying or having the weight of 10,000 kilogram or 10 ton. 3% have the mass of 11 ton, and so on. So I also provided you the weight of the containers. I also provided you with the details about the type of the trucks which are going to carry these containers and transport these containers. We are going to use 3 different types of trucks. One is 8-wheel rigid flatbeds with twin steer and tandem axle dual tires. The other one is tandem axle semi-trailer, and another type is triaxle semi-trailer. And the port management will not allow us to use B-doubles or road trains to access the terminal. So we cannot use those types of vehicles. And this is very normal. The port management can define some limitation for the type of the vehicle. So it is necessary to estimate the number of different types of trucks that will be used based on container size and weight, right? And here you can see the type of the trucks. The first one here is the prime mover. This is the prime mover for semi-trailers. So they can be used for tandem axle semi-trailer and for triaxle semi-trailer. The second one is 8-wheel rigid flatbed, right? So they are not prime mover anymore. They can carry container. And these are some information about the unladen weight as well as the dimensions, the lengths of the vehicle. And these trucks will add to the existing load, of course, on the new realigned road. And at the end, I provided you more information on how to distribute the load between different trucks and between different axles. So eventually in this part, similar to practice, similar to the case that they had for expansion of the Botany port, we are going to determine the design traffic. We want to predict the design traffic, and based on that, we want to design the type of the pavement. So yes, there is one question. If vehicles like BB are not allowed for terminal pavement, then should we count them in when calculating the existing traffic? For the existing traffic, you can count them because they are not going to go to the port, right? That access road is not just going to the port, right? So the final destination is not just the port for this case. So still, the existing traffic can have some B-double or road train. But for the port, for the transport of the containers, it is not allowed to use B-double or road trains. Is this clear? So how to transfer kilogram into ESA? As I mentioned, what you need to do is to determine the different types of the axles, right? And then say that, for example, for this axle, the load is this much. Then, after you determine the load for each axle, you can use this empirical equation, load over a standard load to the power 4 for the rotting mode of failure, for permanent deformation of the road. And change that one, convert that one to equivalent standard axle, right? So the load is used here. That kilogram that you are saying will be used here. Yes. So for container, again, you need to determine the weight upon each axle, right? The same procedure, the same procedure. Any other question? So this example will help you a lot. If you go through this example, the procedure would be similar to this. This is not that complex. So there is another question for the traffic counts, the weekday counts, Monday to Friday traffic counts. So you need to decide whether the traffic is higher for example, weekend, or it is higher during weekdays, how to determine the maximum value, right? When will you upload the assignment description? I already uploaded the material in Moodle. I already put the Excel file for you, and also the description for the trucks. But during this week, I also explain, I will write down the details for assignment 2. I will upload it this week for you. But most of the details are in these 2 files that I showed you. All right. So now we know what is the CBR value for the subgrade, for the type of the soil that we are dealing with. We also know what is the design traffic. In the next step, we want to design the flexible pavement for the access road. So in the first step, we determine the subgrade. We evaluate the strength of the subgrade, the value of CBR, then design traffic, how many vehicles are going to pass through the roads. We converted them to the equivalent standard axle. In the third step, we want to design the flexible pavement for the access road. And there are 2 methods in order to design. One method is the empirical design, which is only for the design of the roads with unbound granular material, and the other one is the mechanistic design, which is the procedure is more complex, but the design would be more rigorous. And for mechanistic design, we need to use the software Circly. So I start with a brief introduction about the type of the pavement. So flexible pavements are widely used in Australia. Maybe almost all the road that you see in Sydney, in Australia, all the networks you see are flexible pavements. We don't use that much rigid pavement for the roads. They are mainly used for example, airfield or industrial floors. And at the top surface of the road, we can either use asphalt pavement, or we sometimes use one surface of bitumen. We call it bituminous pavement. We call this type of pavement flexible. As you can see here, the level of settlement is considerable, and you need to take into account the effect of that level of settlement in your study. And the reason for this large level of settlement during the design life is because this type of pavement has no or negligible flexural strength. So it has low or negligible flexural strength. Therefore, it causes relatively large deformation at the surface. In this type of pavement, compressive stress is transmitted to the lower layers by grain transfer, right? So we are dealing with a granular material, and by using granular grain transfer, we try to distribute the load in a wider area. And we place on a subgrade, you already know that. We need to determine the CBR value for the subgrade or the Young modulus for the numerical analysis or for mechanistic design. If CBR is less than 5, we generally need to stabilize the material in order to improve the quality, in order to make the field ready for construction. And as I mentioned, almost all of the Australian paved roads have flexible pavements. What is the distribution of the stress? So initially we have a concentrated load at the surface. Now in order to distribute the load and reach the acceptable level, we need to use several layers. We use the surface layer. Still the magnitude is large. It is not acceptable for the subgrade. Therefore we use base layer. Again, we distribute the load. Then we use subbase layer. And eventually you can see that when the load reaches to the subgrade level, it is almost a uniform load with a low magnitude, right? So eventually this value should be acceptable and should be the strength, the level of pressure should be less than the strength of the subgrade. So here is the design process. Initially we calculate the CBR value for the subgrade. Then in the next step, we need to choose the type of the pavement, whether flexible or rigid. So for most of the roads, we are designing flexible pavement. Then you need to design and determine how many layers you want to use. You can have, for example, one subbase, or you can even have 2 subbase layers with 2 different types of materials. Then base course, surface course, and wearing course. And for each of them, you need to decide which type of material you want to use, right? Generally, the quality of the material increasing from the bottom to the top layer. So low quality material for subbase, higher quality material for base layer, then the best quality material for surface. And of course, you need to, if you are dealing with a major, an important project, you need to take some samples to the lab and conduct some tests on the type of the material that you are using in order to find the material parameters, in order to characterize the material. We have 2 types of material in the structure of the pavement that we can use. One group are unbound granular material. The other one are bound granular material. Unbound granular material are the material with the cohesion or tensile strength of less than 80 kilopascal, right? So there is not that much strength, tensile strength between them. But on the other hand, for cemented material, as well as for the hot mix asphalt, we know that the tensile strength is very large. It is much larger than 80 kPa. So if the tensile strength is larger than 80 kPa, we call that type of material as the bonded material. For example, for cemented material, we use cement in order to increase the tensile strength, so the particles will stick together because of the cementation. And in asphalt, we are using bitumen in order to increase the tensile strength of the material. But what is the material behavior? In electrodes, we are assuming that the material that we are dealing with is homogeneous, right? So at different points inside the structure or inside the subgrade, we are considering the same material parameters. For example, for point A and for point B, we are using the same material parameters. We assume the material we are dealing with is homogeneous. Also, we are assuming elastic behavior for the material. And this is sometimes it's a big assumption that we are using, because we will have some permanent deformation in the system. But when we want to study, we are assuming elastic behavior, the recoverable deformation. For granular materials with tensile strength less than 80 kPa, we need to consider the behavior as transversely isotropic. We need to consider the degree of anisotropy. And what does that mean? It means that in different directions, the material parameters are different. For example, in vertical direction and in horizontal direction, the values are different. And you remember that generally we consider that the vertical Young modulus is 2 times larger than the Young modulus in horizontal direction. But for bound layers, for asphalt as well as for cemented material, we are assuming isotropic behavior. So in different directions, we have the same material parameters. After you decide about the type of the material and determine the material parameters for each layer, the next step is to determine the traffic load, the magnitude of the load, the pressures, as well as the number of the repetitions. So eventually we need to determine the design traffic. Now you have the design traffic, you know what is the strength of the material, you know what is the subgrade evaluation. Finally, you need to design the structure of the pavement and determine the thickness of the layers, right? So you need to design the most economical pavement structure for your road, for the road. In order to design the pavement and determine the thickness, we should know the distress modes of flexible pavement, the failure modes. The first failure mode is rotting or permanent deformation. This is related to the traffic. This is the traffic associated and is associated with the densification of the material. So if you have a road, if you have a pavement, for example, and this is subgrade, this rotting is considered as the permanent deformation at the top of the subgrade level, at the top of the subgrade layer, right? This is considered as a major failure in the road, and if we reach to that point, we need to rebuild, reconstruct, and design a new type of pavement for the road. So this is associated with the subgrade level, related to the subgrade, permanent deformation of subgrade. The other mode of failure is cracking. And this cracking can be traffic associated or non-traffic associated. For traffic associated, the cracking type or this distress mode is called fatigue. And that's due to the repetition of the load. or it can be because of the low repetition of very large loads, or it can be because of the repetition, many repetition of normal loads. So this is called fatigue cracking, and that's because of the tensile strain inside the bond materials, inside the asphalt as well as cemented material. So the first mode of deformation, the first mode of failure was related to subgrade, and it was permanent deformation. The second one is cracking, and that is related to asphalt or cemented materials. So we call this type of cracking as fatigue. This is the damage occurring when a material is subjected to cyclic loading. We can also have cracking when we have the change in, for example, temperature, or when we have the change in the value of the moisture content. So thermal cycling can cause some shrinkage cracks inside the structure of the pavement. Also, moisture changes can become problematic. And that is mainly for a case that you are dealing with swelling soil, reactive soil. For example, in Western Sydney, we have this type of material. We are dealing with reactive soil. If you add water to that one, it will expand. If during the dry season, it will shrink. And this level of deformation is considerable and can cause failure of the road. The other mode of failure or distress mode is roughness, or it also calls irregularity, and that is because of the variability of density. So when you design a road which is the strength is not uniform, or the material parameters are not uniform, the material is non-homogeneous, and that can cause some roughness. Again, that can cause some permanent deformation in the structure. Ostroads, when we want to use ostroads for design of pavements, these are two modes of failure that we are considering: rotting as well as cracking. So the fatigue cracking, as I mentioned, it starts at the bottom of the bond materials, at the bottom of, for example, the asphalt, and it propagates and extends and reaches to the surface. When it reaches to the surface, we call it reflective cracks, and we see reflective cracks in the road. This is considered as a failure of the road. So if you see a road with this type of cracks, this is considered as a major failure. So this is one mode that we are considering in ostroads, the first mode of failure. The other mode of failure is permanent deformation or rotting, and this one is related to the subgrade, the permanent deformation in subgrade. And this is the permanent deformation along the wheel passes. So you can see at the level of subgrade, we have some permanent deformation. And this is an example of this type of failure in the road. And any pavement you design, you need to check whether this happens during the design life or not. If this happens during the design life of the pavement, then your design won't be acceptable. But which method we need to use for the design? There are two approaches. One is called the empirical design approach. The other one is mechanistic design approach. The empirical design approach is very straightforward, it's very simple, but it is only limited for the design of pavements with granular materials. So it is mainly for granular, it is only for granular pavements with one thin bituminous surfacing or with one thin asphalt layer. So for this one, you do not need to conduct any analysis, any determination of stresses or strains, anything. This is mainly based on past experience in pavement design and investigation. But when you are dealing with a pavement with bound materials, or even for the case that you want to design granular pavement, you can use mechanistic approach. This is more rigorous way and of course more complex way to design a flexible pavement. And for this one, you need to use solid mechanics to determine the stress and strain inside the structure of the pavement and also at the top of the subgrade level. How can we determine these stresses and strain? We need to use some software like Circly. Circly is the software provided by Ostrows for determination of the strains and for the design of flexible pavements. You can, instead of Circly, you can also use numerical methods for determination of the stresses and strains. For example, you can use Abacus, you can use ANSYS, Plaxis for determination of the level of settlement, and in that case, you can even consider more complex constitutive model for your analysis. You can consider, for example, elastoplastic or viscoplastic models. Or, for example, the nature of the load is cyclic, so you can use the models suitable for cyclic analysis. But Circly, as I mentioned, it is mainly based on elastic behavior of the material. So it is very simple program to determine the strains. Also, another software provided by Ostrows is called OSTPaths, and that's an online software that you can use, and that's based on the finite element method. And it is interesting to note that this software was developed in Geotech Group at UNSW for design of pavements, and later this was developed as a part of a ARC project, and later the program was given to Ostrows, and now Ostrows use this software for the design of many roads. So let's start from the empirical design. For the empirical design, this is the chart that we are using. As I mentioned, this is for unbound granular pavements when we don't have any asphalt or cemented material with thin bituminous surfacing. The thickness of this surfacing or the thickness of the surface layer should be less than 40 millimeter, right? If the thickness for the surface is less than 40 millimeter, then you can use this chart for your design. And it is very simple to use this chart. You can learn it in 5 minutes. We are going to work on this, and within 5 minutes you learn how to use this chart. And it is interesting to note that by far most of the roads in Australia have this type of pavement, unbound granular pavements, right? Over 90% of the road that we have in Australia have this type of pavement and can be designed by this simple chart. So we are going to learn how to design unbound granular pavement with thin bituminous surfacing, and that's the type of pavement widely used in Australia. This chart has been developed over 30 years ago, so for a long time it is used in practice for the design of the roads, and it is based on historical observations of in-service pavement and field trials. So there is one empirical equation, and this chart is based on that empirical equation. you can simply use that one to design the unbound granular pavements. How about the surface here? The surface can be a sprayed seal, or it can be one asphalt layer with the thickness less than 40 millimeter. When the thickness is less than 40 millimeter, it is very thin layer, and there is no, that layer cannot be considered as a structural component, right? This won't give any strength, so we ignore the strength of that layer in the analysis. So the surface course is not considered as a structural component for us in this case. So as I mentioned, we don't have any bond material in the structure of the pavement when we want to use empirical design, right? We have base and subbase, and both of them are granular materials. So in this case, the only mode of deformation, the only mode of failure would be the permanent deformation at the top of the subgrade level. And of course, since we don't have any bond material, we do not consider fatigue cracking. And the first layer or surface layer is a very thin layer, so it is not considered as a structural component, so you do not need to check fatigue cracking for that one. Let me show you one very simple example and show you how we can use this chart to design unbound granular pavement. We have the design traffic. It is 2 times 10 to the power 6 equivalent standard axle, and also the subgrade strength is CBR equal to 4. So you remember from the first lecture, this is less than 5, so it is considered as a soft subgrade. Generally, we need to make some improvement, make some stabilization in order to make the site ready for construction. But here we are going to design on CBR4. So it is easy. We have the design traffic. It is 2 times 10 to the power 6. So this is the design traffic. The horizontal axis will give us the design traffic. The vertical axis here on the right-hand side gives us the CBR value for different layers, right? The CBR value for the materials that we are going to use for subgrade, subbase, and base layer. And the vertical axis on the left-hand side will give us the thickness for each layer. There is also one shaded area that you can see here, and that will provide us with the minimum thickness for the base material. So for that design traffic, a specific design traffic, you need to consider at least a minimum thickness for the base layer. What should be that base layer? That base layer should have CBR larger than 30 based on the chart and based on Astros, right? So this is the minimum value of strengths you need to consider for the base layer. Base layer should be a material with the CBR value larger than 30. So we know what is the traffic. It is 2 times 10 to the power 6. We know what is the CBR value for subgrade. It is 5. You simply draw a vertical line until you reach to CBR 4. Sorry, CBR is 4 for this example. And then you read the thickness. So the total thickness of your pavement should be at least 480 millimeter, right? Then you continue this line until you reach to the minimum thickness zone, the shaded zone. And again, you read the value. It is 140. And this 140 millimeter is the minimum thickness for the base layer. And the difference between these two will give you the thickness for the subbase layer, right? So for the subbase layer, the value is 340. The thickness would be 340 millimeter. So this is the final design. This is the profile of your pavement. So minimum base thickness is 140 millimeter, total pavement 480. 480 minus 140 gives you 340 millimeter, which is the thickness of the subbase layer. And this becomes the structure of your pavement when you are dealing with the granular material. And as you can see here, we consider 25 millimeter for the asphalt concrete at the top, which is not considered as a structural layer since it is less than 40 millimeter. So is this clear? Any question? So I'm going to solve another example for you, which clarify everything about this chart. But before that, let's have a break for 5 minutes, and then I will continue the rest of the lecture. During this time, if you have any questions, please write it down, and after the break, I will answer them. All right, so let's continue the rest of the lecture. This time we want to design a pavement structure with one base layer and two sub-base layers. So we are going to use three different types of materials in the structure of the pavement. The design traffic has been given to us. It is 4 times 10 to the power 6 equivalent standard axle. The design subgrade is CBR5, has CBR5. We are going to use granular base material for the base layer with CBR larger than 100 and 2 layers of sub-base. One with the CBR of larger than 30 and the other one with a lower quality, CBR value equal to 15. So the aim is to select the most economical pavement thickness. We want to determine the thickness for each of these layers. But before I solve this one, let me ask you one question. What does this mean? Is it possible to have CBR value larger than 100%? Can you tell me what is the meaning of that? A base material with CBR larger than 100%. Exactly, thank you very much. Yes, this is possible. This means that the material that we need to use for base layer is stronger than standard material. Standard material is a well-graded crushed stone or crushed rock, so we can have a better quality material. Thank you. Now, since all the layers are granular layers, we can again use this chart for the design. The surface layer should have the thickness less than 40 millimeter. We already know that. And we start from the subgrade level. So the design traffic has been given to us. The design traffic is 4 times 10 to the power 6. So it becomes 4 times 10 to the power 6. And the CBR for the subgrade is 5. We draw a vertical line. Then we read the total thickness of the soil. So the total thickness of the pavement is 450 millimeter. So total thickness is 450 millimeter. Then we want to use a material, a granular material with the CBR equal to 15. So the quality is lower than the upper sub-base layer. In this case, you need to continue the vertical line until you reach to CBR 15. And this will give you, this amount will give you the thickness of the lower sub-base level. And 230 millimeter that you read is the thickness of the layers above that lower sub-base. So the summation of the thickness of the base layer and upper sub-base layer becomes 230 millimeter. And then we can use one sub-base, upper sub-base with CBR larger than 30. So again, you continue until you reach to the minimum thickness zone for the base layer. Continue, and the value that you read is 160 millimeter. So it means that you need to consider at least 160 millimeter for the base layer. Then 230 minus 160 will give you the thickness for the upper sub-base layer. So 230 minus 160, it becomes 70 millimeter. And then 450 minus 230 will give you the thickness for the lower sub-base. So it becomes 220. So another approach is to use mechanistic design, right? The mechanistic method for determination of the thickness of the layers. This mechanistic design is based on the layer elastic theory from soil mechanics and or from fundamentals of geomechanics. You remember the Boussinesq theory, that we are applying a vertical load at the top surface and we determine the stresses and strain at different points inside the medium. So the theory that we are using in order to determine the strain here is the extension of the Boussinesq theory. In that case, in Boussinesq theory, we were dealing with one layered material, is a uniform type of material, homogeneous material, but the extension is for layered material, the layered medium. Even though we call this method as a mechanistic method of design, we should note that we still use some empirical equations in that one. So in nature, this is a mechanistic empirical method used in Austrus for the design of the pavement. For the mechanistic design, now we are considering two types of failure mode. One is fatigue cracking related to the bond material, asphaltic as well as cemented material, and the other one is rotting, permanent deformation associated with the subgrade. For the empirical design, as I showed you, we are using CBR value for the design. But for mechanistic design, we need to know what are the elastic properties, right? What is the Young modulus, Poisson ratio, and the shear stress function. So the behavior that we are considering is elastic. This is an assumption we are considering. Also, the material behavior, the material is homogeneous at different points. We consider, for example, for one layer, at different points, we consider the same material parameters. If we are dealing with bond material, like asphalt and cement, we are considering isotropic behavior. But for granular material, we need to consider some degree of anisotropy. And we consider the behavior as transversely isotropic, right? So transversely isotropic means EV would be different from EH. And EV is generally 2 times larger than EH in the analysis. So as I mentioned, for mechanistic design, we need to determine the strain inside the medium and then check whether our design is acceptable or not based on that strain we calculate. That strain is at the top of the subbase, subgrade, and it is at the bottom of the bond materials. But we need to know where, at which locations we have the critical or maximum strains in the pavement structure. The maximum strain that we have are generally either below one wheel or midway between two wheels. These are the places that we get the maximal strain. So we need to check the strain in these two, along these two lines. But for different layers, the critical strain would be different in nature. For example, for asphalt, we need to check the tensile horizontal strain at the bottom of the layer, right? So you remember the beam analysis. We have a large tensile strain at the bottom of the layer, right? When you're applying a load to a beam, for example, right? So the maximum strain is at the bottom of the bond material. That's the reason we need to determine the strain at the bottom of the asphalt layer. The same thing for cemented material. Again, cemented material is a bond material. We need to determine the horizontal strain at the bottom. The third one is related to subgrade and permanent deformation. And the larger level of settlement is at the top of the subgrade layer or subgrade soil. So that's the reason we need to determine at the top of the strain at the top of the subgrade. So there are 6 points inside the pavement structure that gives us the critical strains. We don't need to determine a strain for every point inside the structure, just these 6 points. And then based on these 6 points, we need to determine the maximum value for each layer. So we need to check tensile strain at the bottom of asphalt for asphalt fatigue, at the bottom of cement layer in order to avoid cemented material fatigue, and at the top of the subgrade for avoiding rotting and shape loss of the pavement or permanent deformation. And as I mentioned, in the horizontal direction, the maximum strain is either beneath one wheel or it is midway between 2 wheels. How can we calculate the critical strain? We can use the software Circly. And later next week, I'm going to explain you how to determine this one. Either me or my demonstrators are going to explain you how to determine this one based on the linear elastic theory and by using the software Circly. There is one deficiency in Astros, and that deficiency is related to the granular material for the mechanistic design. So when we have, for example, one sub-base layer or base layer, which are granular materials, as you can see in Astros, we don't define any distress mode in the design, right? So in Astros, we don't define any distress mode for granular material inside the structure of the pavement. In Ashto, we have some distress mode because the failure of the pavement can be because of the poor quality or because of the variation of density of granular material. But we ignore that one in Astros. So this is considered as a major deficiency of the approach. No critical response for unbound granular layers. This is a big deficiency we have in this method and in this standard. So this is the procedure for mechanistic design. Initially, we start from site investigation. We conduct different types of tests. You're already familiar with that one. For assignment 1, you worked on that one. Different type of tests, DCP test, CVR test, and so on. And we determine the design subgrade CVR. After that, you can predict the traffic, the design traffic. Then you need to decide about the material you are going to use, conduct some tests in the laboratory to determine the material parameters for those material. Also, during this case, you need to consider the availability of those materials and also the cost of those materials to decide which type of material you want to use for your pavement structure. So all of these 4 are the input data. These 4 are input data. Now, based on them, you need to consider a trial pavement structure, right? You say that I want to consider 2 sub-base layer, 1 base layer, and 1, for example, thin pavement concrete at the top. And you need to decide about the thickness of the layers. So that would be the trial pavement structure. Then you need to check whether that trial is acceptable, whether that is economical or not. So the procedure is like this for checking the acceptability of the pavement structure. So you need to determine the strains, 6 critical strains inside the structure of the pavement by using, for example, circling. After that, you need to determine the pavement reliability, the project reliability, the importance of the project. So this pavement reliability depends on the importance of the road, the average annual traffic, daily traffic of the road. Then, based on this, you need to check 2 distress modes, 2 modes of failure, fatigue resistance as well as their rotting or permanent deformation. If the design is acceptable, if these 2 modes do not occur during the design life of the pavement, then your design can be acceptable. Still, you might need to optimize your design, right? Maybe the thickness that you're considering is too much. So you can decrease the thickness of the layer to see whether your design still would be acceptable or not. So if rotting and fatigue won't occur inside the structure during the design life, then your design would be acceptable. Otherwise, you need to make some modifications in the trial pavement structure. How can you make some changes here? In order to make modification, there are 3 ways. One is that you get back to subgrade. Let me change the color. One way is to get back to the subgrade and try to improve the quality of the subgrade, right? So, for example, you can stabilize the soil. CBR is increasing, therefore the design might be acceptable. The other one that you can change is related to the material that you are using. So you can use higher quality material for different layers, sub-base and base, for example. And the other one is changing the thickness of the layers, right? So you can change the thickness of the layers. You can increase the thickness of, for example, base layer and check again to see whether your design is acceptable or not. So 3 different methods for improving your design. But still, there is one thing that I didn't explain you and I didn't tell you here. How can we check whether fatigue and rotting take place in the structure of the pavement or not? We want to know how to check this one. In order to check this one, we need to use some empirical equations. So you remember, when I explained mechanistic design, I said that this is mechanistic empirical design method in nature. So this is the part that we are using some empirical equations. What are these empirical equations? These empirical equations are related to subgrade and bound materials. The first equation is this one. This equation will give us the allowable repetition, the number of the repetition of the load, right? So you know what is the design traffic. You can determine the allowable repetition based on this empirical equation, and then you need to compare these two. If design traffic is larger than allowable repetition, it means that rotting will take place during the design life. So your design won't be acceptable. But if design traffic is less than allowable repetition, then your design can be acceptable. Why do I call it can be acceptable? Because you need to check whether your design is economical or not. If there is a big difference between these two, probably your design won't be economical. You can still decrease the thickness of the layers, for example. So it is simple. This n, or allowable repetition, is the function of the strain, that critical strain that we calculated by using circling at the top of the subgrade level. You can simply calculate the strain, put it in this equation, determine the allowable repetition, compare it with the design traffic to see whether rotting takes place in the structure of the pavement or not. So this is vertical strain, and the unit is microstrain for this one, and n here is the allowable number of standard axle repetition. So the unit for this one is ESA, equivalent standard axle. And for optimum thickness, the allowable repetition should be either equal or slightly larger than the design traffic, right? In order to make your design optimal. And if allowable repetition is less than design traffic, then your design, your trial pavement structure won't be acceptable. So you need to change your design. We have the same approach for different layers. Again, for asphaltic fatigue, in order to check that, Astros provide us with one empirical equations which give us the allowable repetition, right? So for asphalt, in order to check whether cracking occurs, fatigue occurs in that layer, this is allowable repetition, and you need to compare that with the design traffic. What are the terms in this equation? This is a strain in terms of microstrain. This is the Young modulus of the pavement. This one is the reliability factor. VB is the percentage of bitumen in asphalt. So you can see when the amount of bitumen or percentage of bitumen increases, the allowable repetition will increase, right? The other one is the reliability factor, RF. We also have another factor which is called shift factor or a scale factor, and that's because of the scaling we are using in laboratory tests, right? So this shift factor is between laboratory and in-service fatigue lives. Because when you conduct a test in lab, the boundary conditions, the geometry of the pavement, the asphalt you're considering is different from what you have in the site, in the field, right? So you need to apply some scale factor to the system. This scale factor, there is one presumptive value for that, and it is 6. So we generally use 6 for this shift factor or scale factor. There is also one N, which depends on the number of individual axles within the axle group, right? For example, for a tandem axle group, we know that there are 2 axles, therefore N becomes equal to 2. So again, if allowable repetition is less than design traffic, then fatigue cracking in asphalt, therefore your design won't be acceptable. How can we determine this reliability factor? The reliability factor is the chance that the pavement being considered will outlast its design. And of course, when we are dealing with an important road with high level of traffic, you need to consider higher level of reliability factor. For example, for freeway with a large level of traffic, with a large design traffic, the project reliability is 95 to 97.5%. For highway with annual average daily traffic larger than 2,000, this project reliability is 90 to 97, and you can see the values for different types of the road. So the project reliability depends on the design traffic, the value of the traffic load. And this is the table you can use in order to read this RF parameter. For example, for freeway, the project reliability, the desired project reliability is 97.5%. Therefore, RF should be equal to 9. Again, we have the same thing for cemented layer. For cemented layer, there is one empirical equation which gives you the allowable repetition. You need to compare that with the design traffic to see whether your design is acceptable. So here, this term is the S-strain. This term is related to the reliability factor, and this is the number of the axles within the axle group. And this is the table you can use in order to determine the reliability factor. Again, for freeway, the value you need to consider is 0.5, right? So when the project is very important, when the level of traffic is very high, you need to consider lower value for RF, which means that the allowable repetition is less. So you need to increase the thickness of the layers. In this equation, there is another term, which is called fatigue constant. And for fatigue constant, there is an equation. That's the function of the flexural strength and the Young modulus of the material, the cemented material that we are dealing with. So by having the Young modulus and flexural strength, you can determine the value of fatigue constant. Also, there is one maximum value for this K. There is a cap for this value, so you cannot increase this value beyond K max. And that's, again, there is one empirical equation for that one, and it has a inverse relation with the square root of Young modulus. For fatigue cracking, we know that if allowable repetition is less than design traffic, then fatigue cracking in cemented material will take place, right? Does it mean that we need to change our design? Here, the answer is no, right? Sometimes fatigue cracking is acceptable inside the structure of the pavement. That is the case that the asphalt cover is larger than 175 millimeter. So if the thickness of the asphalt layer is larger than 175 millimeter, then you can consider a secondary life for the pavement, right? So we have crack inside, so there is no tensile strength. The material, the cement material, won't have any tensile strength anymore. And in that case, during the secondary life, the material behaves like a granular material, right? So you need to determine the allowable repetition for two cases. One pre-cracked phase, when we have a cemented material in the structure, and the other one is post-crack phase. And for post-crack phase, instead of the cemented material, you need to use unbound granular material. And for this unbound granular material, Ostrows tell us to consider the vertical Young modulus of 500 MPa. This is only for the case, you can consider this post-crack phase only for the case that the asphalt cover is larger than, or the cover above the cement is at least 175 millimeters. Now let's consider that for sub-base layer or base layer, you want to use unbound granular material, and you want to use the mechanistic design. In that case, the stiffness of the material, the Young modulus of the unbound granular material, is affected by the lower strengths of the subgrade. We know that for unbound granular material, the modulus, the Young modulus, is the function of the stress. And also it depends on the stiffness of the underlying layers. So at different points inside the unbound granular material, we will have different strength values. And for mechanistic design, we need to take into account that effect. How can we take into account this effect? We need to use sublayering technique. We need to divide the unbound granular layer into several sublayers. And for each sublayer, you need to determine the Young modulus and the elastic properties. The maximum Young modulus will be for the top layer in this case, because this is far from the subgrade. And the lowest one is for the layer adjacent to the subgrade, next to the subgrade. So the strengths of the material, unbound granular material, will be affected by the subgrade soil. How can we determine this one? Ostrows tell us to divide the thickness of the layer into 5 sublayers, right? So we divide it to 5 sublayers, and then we can use these empirical equations to determine the value of the strengths for each sublayer. And that depends on whether we are talking about the selected subgrade material or we are talking about sub-base or base layer. For base and sub-base, these are the equations that you need to use. And for the subgrade selected or improved subgrade materials, these are the equations that you need to use. So I'm going to show you how we can use these equations in an example. It would be easier. We are going to use sublayering method to determine the strengths and the stiffness Young modulus for unbound granular material. What is the structure of the pavement? There is one subgrade with the CBR of 3%. We already know that this is very low value, so probably we have difficulty for the construction of the pavement. So prior to any construction, we need to improve the quality. But anyway, we consider 3% for the subgrade. Then we are going to use unbound material with the Young modulus of 200. And at the top, we are going to consider an asphaltic layer. It's the Young modulus of 2,500 MPa. We want to know what should be the Young modulus for the unbound granular material. So in this case, the first thing we need to do is that this is for the base and subbase layer. We are going to use these equations. This will give us, the first equation will give us the vertical Young modulus at the top of the granular sublayer, and define this one as the function of the vertical Young modulus of the subgrade. We also need to read some presumptive values provided by Ostrows and pick the minimum value. So the first thing we want to do is we divide unbound granular layer into 5 sublayers, and then for the top layer we want to determine E top. The vertical Young modulus for subgrade, we know that CBR is 3. You can simply multiply that with 10 and you can determine the Young modulus. It is 30 MPa. Then we use that empirical equation to determine the Young modulus for the top layer. It becomes EV subgrade, which is 30 MPa, multiplied by 2 to the power of total granular thickness divided by 125. So we use this empirical equation. Subgrade strength, subgrade stiffness is 30. Total granular thickness is 200 millimeter. So the value that we derive is 91 MPa, right? The question also gave us that the material has the Young modulus of 200 MPa. So we have, so far we have two values, 200 MPa and 91 MPa. There is also one table in Ostrows that we need to check to see what is the presumptive value for this material. It says that what is the thickness of the overlying material in this table? The thickness of the overlying material is 200. So I consider 200. And also it asked what is the modulus of the cover material. So the modulus of the cover material is asphalt here. The modulus of the cover material is 2500 MPa. So 2500 is between these two. The value that you read for both of them is 150. So table will give us 150 MPa. The question gave us 200 MPa. And this empirical equation gave us 91 MPa. So which value we need to consider? We need to consider the minimum value, 91 MPa, for the top layer. Next step is to determine this reduction factor, this ratio of stiffness, decrease in stiffness of the unbound granular material, right? So this ratio factor is the function of the E top, which is 91, and E subgrade. And E subgrade we determine 30. So it becomes 30. So E top 91. The ratio is 91 divided by 30 to the power 0.2, and the rate of decrease in depth is 1.25. Now how can we determine? For the bottom layer, you can simply multiply the Young modulus of the subgrade by this reduction factor to the power 1. So it becomes 37. For the second layer from the bottom, you can multiply the subgrade Young modulus with the reduction factor to the power 2, third layer to the power 3, fourth layer, and fifth layer. So these are the values from the bottom to the top. This is 37. This one is 46. This one is 58. And the final one is 91. And this is 72. We have the Young modulus in vertical direction. Then based on that, you can, for example, easily calculate EH, 0.5, for example, times 37 for the bottom layer. All right. So is this clear? Everything clear? So let me show you another example. This time we want to go through the whole mechanistic design procedure and design a pavement. All right. So what is the example? The design subgrade CBR is 5%. So we know what is the CBR value. The design traffic for 30-year design life is 10 to the power 7 heavy vehicle axle group. The traffic distribution is in accordance with the presumptive urban distribution. So we are going to use presumptive values for traffic distribution. And we will plan to design a sprayed seal surfaced unbound granular pavement. Unbound granular pavement is a thin bituminous surface. So we are going to follow the Oster's procedure. The first step is to consider a trial pavement structure. So we assume the first layer, surface layer, doesn't have any structural contribution. Therefore, we can consider something like 20 millimeter thickness for the first layer. No thickness, no structural contribution. But for unbound granular material, we are considering 475 millimeter thickness, and then we have a semi-infinite medium, which is the ground, with the CBR 5%. Next step is to determine the elastic properties. Unbound granular material, it's an unbound granular material, therefore you need to consider transversely isotropic behavior, right? It is not isotropic. So subgrade CBR is 5% for subgrade. So initially we determine the material parameters for subgrade. And subgrade is again granular material, therefore you need to consider anisotropic behavior for that. Vertical Young modulus becomes 50 MPa, simply 5 times 10, 50, divided by 2, 25 MPa horizontal Young modulus. Here we assume that we are dealing with a cohesive soil. So for cohesive soil, we are considering 45, 0.45 as the Poisson ratio. Same value in both directions. And eventually we determine the shear stress function, which is the vertical Young modulus over 1 plus Poisson ratio. So in the second step, we determine the material parameters for subgrade. We cannot use CBR. We need to use elastic properties for mechanistic design. Now for the granular layer. It's a granular layer, therefore Young modulus is changing in depth. So we need to divide the whole layer into some sublayers. And based on Oster's, we need to divide it to 5 sublayers. So I'm going to use, for the material, I'm going to pick the material properties from the presumptive values provided by Oster's. So this table that I'm selecting from Oster's is providing the Young modulus for granular materials unbound granular materials under thin bituminous surfacing, right? So I'm using this one. And here I am assuming that for the road, I'm going to use high standard crushed rock, right? What is the typical modulus for this one? It is 500 MPa. And since we are dealing with granular material, it's cohesionless material, therefore Poisson ratio is 0.35. You can also simply calculate the value of F based on this equation. Again, the material is unbound, therefore the behavior you consider should be transversely isotropic. That is the reason we are considering the degree of anisotropy 2. For isotropic material, the degree of anisotropy is 1. This is the ratio of the E vertical to E horizontal. Next step is to use this empirical equation to determine the Young modulus for the top of the base layer, right? So it becomes EB for subgrade. We already calculate that one. EB for subgrade is 50 MPa. 50 2 to the power total thickness of granular material, which is 475 millimeter, divided by 125. That will give us 696 MPa. Now we want to determine the Young modulus. Once we use this empirical equation, the other one is the presumptive value we read from the table, which is 500. We need to pick the minimum value. So the minimum value becomes 500 from the table. So Young modulus, vertical Young modulus for the top layer of the unbound granular material becomes 500 MPa. Degree of anisotropy is 2, so you simply divide this one with 2. That will give you horizontal Young modulus. Granular material, Poisson ratio 0.35. Using this equation will give you F. So now we want to determine the Young modulus and material parameters for different layers. We divide it to 5. So we will have 5 sublayers with 95 millimeter thickness. The Young modulus of the subgrade is 50. The top layer we calculated 500. The Young modulus of the top layer. Now we need to calculate that ratio of moduli, right? That reduction factor. So 500 divided by 50 to the power 0.2. That will give us the reduction factor of 1.585. We generally start from the bottom. So 50 times R will give you the value for the first layer. 50 times R to the power 2 will give you the value for the second layer, to the power 3, third layer, to the power 4, fourth layer. So these are the material parameters, the vertical Young modulus you need to consider. And based on that, again, unbound granular material, degree of anisotropy is 2. So simply divide EV with 2 to determine horizontal value. So eventually, this becomes the set of the material parameters for different parts of the pavement structure. You start from subgrade, and then 5 sublayers for the granular, unbound granular material. In this example, there is no bound layers, so we don't need to consider the bound layers, cement and asphalt. Then we go to this empirical equation to determine the allowable repetition. So this is the empirical equation we need to use. We already know the term. We know what is the design traffic. It is 10 to the power 7 heavy vehicle axle group. So NDT is 10 to the power 7 heavy vehicle axle group. We need to multiply this one with the damage index. You remember that when we want to determine the design traffic? What is the damage index here? From the presumptive value, it is 0.7. Damage index, NDT, you simply multiply damage index with NDT and you determine the design traffic. The design traffic becomes 0.7 times 10 to the power 7. In the next step, we need to determine the S-trains. So since this is a long example and it is already 8 p.m., let me continue the rest of this lecture in the next lecture next week. And again, I briefly start from the beginning, explaining this example for you, and then I will tell you how you can determine the S-train inside the structure by using software Circly. So do you have any questions regarding the mechanistic design or empirical design method, or about the previous part about the design traffic? All right, if you don't have any questions, that's all for today. I will continue the rest of this example. I will solve it for you next week. Thank you, everyone. Thank you.